So what's an optimization problem? It's basically it's very similar to the problems we saw earlier with our word problems, except these are slightly different. In these, we're trying to kind of optimize something. We're trying to find the max or the min of something instead of try to find the rate of change at a certain time. We're trying to find when this rate of change is kind of the best. So when is it? Basically when we have our derivative to be a critical point. And so these are basically going to be the 6 same steps that we use to do these. Remember to go slowly. And the 6 steps for this is almost the same as the last 6 steps. Understand the problem, right? Second, we draw a diagram. So these are all things you should now remember from when we're doing our rates of change stuff. 3 is we introduce notation. 4, we express desired values in terms of other things. So we make equations of other things. Find relationships between variables. So that each variable so that equation is in one variable. Sorry, my handwriting is not amazing on tablets. I'm still trying to figure out how to write neatly on these things, but I'm trying. And then finally, we're going to find absolute, max, and min. So the reason we're trying to find absolute max and min is because this is how we optimize something, right? So if we want the best of something, we want the absolute max, not the local max. We want when is it literally the best. And so these are the 6 key points we're going to do. Notice how this is very, very, very similar to what we had done with the word problems. So what are these problems going to look like? You guessed it, they're going to look exactly like word problems. So let's look at an example. So this example, we're traveling to the 18th century. We time traveled and somehow got stuck in the countryside of some kingdom. Our time machine broke down, basically. And looking at our time machine, we realize it's going to take up to a few years until we can fix it, right? These things are a little complicated, and we can't just punch in a few digits for it to start going up. We have to actually make supplies and blah, blah, blah. But since it's going to take a few years to get all the supplies, we're going to need to make do and actually set up camp for a little bit. And so we're going to set up a little farm to sustain ourselves. And so what we're going to do is first we construct a cabin. That's not too shabby. And it's like, okay, well, let me just use the material that I have left in order to make crops. So you're going to make some big massive fence. So you're going to take whatever material you have left and you're going to make a fence to protect your crops from animals, right? Because this is back in the 8th century. There's animals roaming around. Wolves are out to hunt you down. And so what we're going to want to do is we're going to want to protect things. So what you have is material to make 400-meter fence. And you can't get more material because this is life. This is just our word problem. And so that's it. And so to help your plot bigger, you decide that one side of the rectangular plot of land will be shielded by a river that looks larger than Lake Ontario. So it's a pretty massive river, yeah? And so the question is, what are the dimensions of your farm which give you the largest area to farm in? So step 1, right? So step 1 is we understand problem. So what does this mean? Is that we reread the problem, right? So we had talked about this before, with problems like these, go slow, read the problem, read it a second time, and highlight the key points. So let's highlight the key points. The first few part is not too much information, but what you do see is you have material to make a 400-meter fence. So this gives you a number, 400-meter fence. So you have 400 meters of material. This thing is so massive. Let's see if hopefully 20 is better. Okay. right? And what you're going to want to do is you're making a rectangular plot of land. Will be shielded by a river. So on one side you have a river. And the question is, what is the largest area? And they're asking particularly what are the dimensions of your farm. So let's start number 2. Number 2 is to draw a diagram. And so I have colors. So hells yeah, I'm going to use colors. So we have some river. This is some awesome river. We'll add a little fish. Bloop. There's a little fish. We'll do this fish backwards. We can even have a little bear on the other side of the river. Rawr. Little bear. Bloop. Okay, anyway, I'm done drawing. And so what we're going to want to do is we're going to want to make a plot of land, right? And it's going to be rectangular. So we know our plot of land is going to be a rectangle. So we'll have something like this. Here we'll have a little house. And here inside we have little crops. In an exam, I'd recommend you not do this much drawing. But this is not an exam. I mean, I guess you have more time on exams now, huh? So maybe a drawing like this would be fun. If you want, you're more than welcome to do a drawing like this. So this is what your plot of land kind of looks like. Next, we're going to introduce notation. So one thing we'll have is we'll make one side width, one side length. So width, W is width, L is length. P will let be perimeter. A will let be area. And I think that's all we need. That should be okay. Okay, so now let's say what do we want? We want the dimensions. And so we have some information, right? So we have perimeter, P, is equal to 2 times width plus L, right? So we have 2 width. So we have one width on top, one width on the bottom, and we only have 1 L. And that's because the other side is the river. So we don't need a fence. The bear is not going to be able to swim across this fish-infested water. And even if it does, it's going to be distracted by all the fish. So we're okay. So we have that the perimeter is 2W plus L. But what's the area? This is what we're trying to solve. So I guess this is technically, 4 and 5, so what's the area? The area is width times L, right? And so what we're going to want to do is express what we want. I guess this is 5. Maybe 5 and 4 I should switch. But we're going to want to express the desired stuff in terms of... No, I guess it's okay. So this was 4, yeah. I'm looking at my notes, yeah. Okay, this is 4, sorry. 5 is to express these things in terms of one variable, right? And so what we're going to want to do is we're going to want to convert A to be one variable. So how do we do that? One thing we know P is equal to 400, right? Because we are told 400. So basically here, I'm going to do like a little check mark whenever we use something. So we just used 400. We used rectangular piece of plot. We used shielded by a river. And so we have P is equal to 400. So basically what we have is 400 is equal to 2W plus L. And we also have A is equal to WL, right? And so what we want to do is solve for A, but we only want one variable. So let's plug this into this. And which way did I do it? Yeah, we did it that way. And so what we can do is this will give us L is equal to, let's move the 2W on the other side. And we get 400 minus 2W. Yeah, and so we can plug this in, and we get A is equal to W times 400 minus 2W. So this is just 400W minus 2W squared. Okay, so what we're going to want to do, so this is 5. That's it. So what's next? What we're trying to do is find the largest area. So if we think of our area curve, so we'll do this on the side. So if we think of our area curve, right, it's going to probably be something like this, right? If we have some really thin piece of land, it's going to be very small. This is going to be when it's horizontal, and here is probably where it's going to be more square-ish. So our graph is going to be something like this, if you think about it. And so basically what we're going to want to do is look where we have somewhere where the derivative is 0. So what we want, where is derivative 0? Derivative equal to 0, and concave down. So what we're going to want to do is take the first and second derivatives. So the first derivative, a prime, with regards to w, right? So aw, so here actually we'll do this, dA dw is equal to, so here w is my variable, so I'll have 400. All right, a on top, just so we can kind of see what's happening. 400 minus 4w. And then the second derivative, so d dw of dA dw, which this, remember, we can just write as d squared dw squared of a. This is just the second derivative of this, so we get minus 4. Okay, so when is a prime 0? So this is 0 when we have 400 minus 4w, or when 4w is equal to 400, or when w is equal to 100. So this is when the derivative is equal to 0. And let's double check that our thing is concave down. And actually, we don't even have to plug things in, right? We see our function is always concave down. We have minus 4, which means we're always in this kind of down shape. And so we really only have to look at this. So we have critical points in, so we have 3 different, remember when we're trying to do the absolute max, we need to calculate at 3 different points. When w is 100, right, this is our crit points. But also when we have, what our interval is, right? So what's the smallest our w can be? Our w can be 0, right? W is equal to 0 is the smallest. So we'd have basically a fence that is just massively long but has no width. This would obviously have 0 area. And then if our width, if instead we make our fence sideways, right? But remember that we have 2 widths, the max width can be 200. So these are all 3 places that we need to test our graph, right, in order to calculate whether or not we have an absolute max or not. So what we have to do, we plug these into our function a. So remember, this is 400w minus 2w squared. And this is where a calculator would help. A of 0, this is just going to give us 0. A of 200, this is also going to give us 0, right? And then finally, A of 100, this is going to give us 20,000 as our number. So basically we have a 20,000 meter plot of land, kind of. And so this is when we have our maximal thing. So this is our largest area. This is done, equal largest area. But we still have the question of what are the dimensions, right? So the dimensions we're asking is what is W and what is L? So we have here we already know what W is. So we know W is equal to 100. But what's L? L is equal to 400 minus 2W, right? And we saw this earlier. So plugging in 100, we get 400 minus 200, or 200. So we have 100 by 200. And I think we have more room, yeah. 100 by 200 is our dimensions and our final part. So I'll stop here in the sense that next you have another question to do the same thing. So I'll give you some time. You should pause the video. So pause the video. And try this one. You should take this should take a little longer. This should be about 10 to 15 minutes. And then when you come back, I'll just finish this up in this video, so that we're not, and then we'll end it for today, so it's not too long, since this problem does take a while. So go and try it. Pause the video. All right. Hopefully you pause the video and tried it out. And so let's actually try to figure this out, right? So what we're trying to do is we're trying to minimize our surface area. We know we have 250 milliliters of Coke. We know the volume of the can is 250. We know we want a cylindrical shape. And I actually tell you how to calculate the surface area, right? So let's look at our key points. So that was 1. 2, a can of Coke is going to look like a cylinder, right? So we have something like this, where this is going to be H for height. This is going to be R for radius. So we have R, so this is 2. Part 3, we have multiple variables, right? So we have R, H, we have T is time. Why do I have T? What's my T? That should be H. Yeah, that's H. Okay, my notes are weird. H, we have A is area, and V is volume. Yeah? And we know, so part 4, we know area. The surface area is given here, can be calculated by calculating the area of the 2 circles. So we have 2 tops, right? So we have pi r squared. Then adding the surface area of the cylinder part. So what's the cylinder part? That's just the circumference times the height. 2 pi r h. This is something I would kind of expect you to be able to find or look up. So I would give you some hints like this for future. The volume, this is just the volume of the can is the same as the area of the top times the height. So this, basically, I told you what it is. It's the area of the top, pi r squared, times the height. So we have this. And so now we're going to try to solve things in regards to by putting everything into one variable, right? So we know volume. So volume is equal to 250, right? We were told this. So volume is equal to 250. And so let's try to keep only one variable. And we're going to try to keep R, because here I notice I only have one H, so it'll be a little easier. So we're going to say 250 is equal to pi r squared H. So we'll make H equal to 250 divided by pi r squared. And so that gives us that the area is equal to pi r squared plus 2 pi r h, which is 250 over pi r squared. So the pi's cancel. We have an r and an r here. So really we have pi r squared plus 2 times 250 is 500 divided by r. Oh, dear Ram. Okay, I screwed up in my notes. Somehow I said 2 times 250 is something else. Okay, anyway, so we have this as our area. And so now what we're gonna want to do is to find where this, so what else did we do? We did cylindrical shape. I guess we don't need this. This is extra information. We're gonna want to minimize surface area. So basically what this kind of means, right? So we should have some graph like this. So let's take our derivatives and kind of see what happens, yeah? So what you should have gotten is a prime. So this is part 6. A prime should have been 2 pi r. Wait, this is off. This should be 2. Right? Because we have 2 circles, one on top and one time on the bottom. So that was my fault. Sorry. God, none of you told me. No, I'm joking. So we have 4 pi r, right? Because the 2 comes in front. And then here we have minus r, minus 500 over r squared. This is what you should have had. And so technically we can actually move this into one formula if we wanted. 4 pi r. So here I can multiply by r squared over r squared to get 4 pi r cubed minus 500 over r cubed. Yeah. And so now let's look at the second derivative. Or actually, no, we can solve this part right away. So when is we want to know when we have a critical point, right? So when is a prime equal to 0? I guess I should not be writing a prime, huh? I said this is better to do this. So when is dA over dr is equal to 0? And basically this is equal to whenever this is equal to 0, right? 4 pi r, this is squared. 4 pi r cubed minus 500 over r squared is whenever this is 0. R can never be 0, so r is not 0 in this case. It's whenever the top is 0. So it's whenever 0 is equal to 4 pi r cubed minus 500. Right? It's whenever this top part goes to 0. And so what we have is it's whenever 4 pi r cubed is equal to 500. In other words, whenever pi r cubed is equal to, what's 500 divided by 4? This is equal to 250 divided by 2 is equal to 125. So let's actually do this together. So we'll do r cubed is equal to 125 divided by pi. I'll bring the pi over as well. So we have this, and actually 125 is equal to, I can't write, 125 is equal to 5 cubed. So this is actually, so r is equal to the cube root of 125 over pi, which actually is just equal to 5 times the cube root of 1 over pi. So this is what is one of our crit points. So this is a critical point. But we also want to make sure, we also want to see when we have, right, we want something that's concave down, because it doesn't matter if it's a crit point if we have something like this. If we have a concave up and it's a crit point, we're maximizing. We don't want to maximize. So we need it that it needs to be concave up. So let's look at the second derivative. So d squared a over dr squared. So remember, this is just equal to d dr of d dr of a. So this is just the second derivative of this function. And I guess maybe for us, taking this top one is going to be easier. So what do we have? We have 4 pi plus 2 times 500 over r cubed. So this is what you should have gotten for the second derivative. And notice how in this case, since r cannot be a negative number, since r is greater than 0, this implies this implies is always greater than 0. And that means we always have a concave up function. So our function does look exactly like this and not like this, right? So we have this and not this. Go away. And not that. And so we do know that this is our critical point. And then that implies that we're going to have a minimum here, right? So this actually gives us our minimum value. So basically, what are we trying to calculate? What are the dimensions of the can? So I should have highlighted this. What are the dimensions of the can? So let's calculate this. But we need r to be 5 times the cube root of 1 over pi. What's h? H, if we recall, this we solved earlier. Bring this down. So we get 250 over pi r squared. So this is just 250 over pi times 5 cube root of 1 over pi, squared. So we get 250 over 25 pi over cube root of 1 over pi squared is equal to the 250 and the 25 cancel, so we get 10 over pi. And then I'm going to convert this into a fraction, so we get pi over 2/3. Here I can add, so we get 10 over pi to the 5/3. So this is our height, this is our radius. And that gives us the dimensions in, I think, I don't actually say the thing. So this gives us the dimensions for our can. So we're actually going to stop here for today. If there's any questions, let me know. As always, I'm available on Discord for any questions during class time. If not, you can also email me. Email or Discord me questions. Email or Discord me questions. All right. Hope you have a phenomenal Wednesday. Yeah, tons of love, and I'll see you all around. Bye.